Welcome. So, we are in the module 7. So, this is the last lecture of the module 7 where we are essentially solving some problems in the Flexure involving the elasticity approach and specifically the stress function approach. So, in the last class we were discussing about this problem where the stresses stress boundary condition, using stress boundary condition we have found out the stresses, and the stress boundary conditions are those which is sigma r theta r equals to a and b equals to 0 and sigma r equals to a and b equals to 0, which means that along these two radial surfaces, radial boundary surface, there is no shear stress as well as there is no normal stress. So, and also the third condition that we are using, so T is essentially 1, we consider it's a rectangular narrow cross section. So, this becomes P, the force, the resultant shear force at here is essentially sigma r theta dr for theta equals to 0. So, with these three boundary condition, what we have achieved in the last class is the finally approximating a stress function. So, the stress function is of following form. So, this stress function is of the following form, and then which is a function of r and theta, the general r theta, but we have used separation of variable where this is a function of r and this is a function of theta, which is the function of theta becomes sine theta. This is motivated from the bending moment equation. Add bending moment formula at any cross section of that beam. So, now this is motivated from the strength of material solution, which is similar to the rectangular case. If you remember the rectangular case, we were using stress function of something like a by 6 xy cube or something like that. So, essentially the stress is xy something in this form. So, essentially the stress is actually del square phi by del y square in the rectangular case. So, this similar so this is the px is the moment. So, this becomes the moment, this part becomes moment, and my by I, something like that. This form was chosen. So, similar with this similar concept here also we choose the sine theta. So, now with this approximation of the stress function phi, we found out sigma r which is of this form, and sigma theta theta which is of this form, and sigma r theta which is non-zero which is of this form. Now, these two thing once we have found out, our next job is to find out the strains and displacements. So, these are the constants which we have used to find out the which we have used to find out the stresses. We can now find out the stresses with the known value of these constants, and these constants are essentially found out by using the stress boundary condition. Now, like in the previous cases, in this case also we have to find out the displacement. So, how to find out the displacement? We have to use the stress strain relation, which is specifically the strain stress relation, or using the compliance matrix or Hooke's law. So, here the strain epsilon r is del u by del r is essentially 1 by E sigma r minus nu sigma theta theta. So, this is epsilon r, similarly epsilon theta theta. So, epsilon theta theta it is better to write it in this form, that del v del theta, del v del theta equals to r epsilon theta theta minus u, and epsilon theta theta again I can write r by e into sigma theta theta minus nu sigma r minus u. So, this form because we will be integrating these equations to find out v. Now, here del u by del r is essentially this. So, now what we will do, we will substitute sigma r sigma theta theta in these two expressions and then integrate to find out u, integrate to find out v, and then we substitute this here, these shear strain likewise in the previous case. So, we will do, once we know the expression of u, once we know the expression of v, we substitute it by taking the derivative with respect to theta of u and derivative with respect to v of r, and then substituting v by r, and then sigma r theta we know from our stress solution. So, with this we can find out the conditions. So, now the same thing we are doing here. Here del u del r I use this and we can now after some manipulation. So, these manipulations we have not shown here. So, this you can just do and check this manipulation. So, this becomes the del u del r. Again, similar to integrating this equation, we can get the expression for u. Now, integrating with respect to r, so this is f theta. So, because as in the previous case also, u is a function of r and theta, and v is a function of r and theta. So, we are integrating with respect to r. So, it will be constants will be f theta. Similar to that, we get a v which is del by integrating this equation, del v by del theta is r by e into sigma theta theta minus nu sigma r minus nu sigma r minus u. So, you substitute u here and sigma theta theta and sigma r you substitute from the previous stress expression, and then you integrate with respect to theta, and then you get a constant which is fr. So, capital Fr, which is a function of r, because v is a function of r and theta. So, now this expression is very long expression. So, now after substituting these two expressions in the shear strain, so essentially this is the expression, we get this kind of equations. So, again these is some of them are function of theta only, some of them are function of r only, and this becomes a function of theta and r. So, you see this d is a constant which actually we need to plug in and see. So, in the similar manner in the previous cases we follow. So, we can just now solve this problem by in a similar manner. So, if I just now assume that if r is hr and f theta is of this form, then we can directly solve this problem. So, the d is a constant. Remember here d, a, b, d, we had three constants which we have already found out from the stress boundary conditions. But these stress boundary conditions are not this stress through this stress boundary condition we found out a, b, d. But we have here three more constants which are h here, k here and l here. So these three constants are the new constants we have invoked into it, and this also gives us u and v. I have written the expression for u here, which is pretty long expression, and then similarly we can write it in the v also. So the boundary conditions has to be used, and those boundary conditions is essentially will be the displacement boundary conditions. Now these displacement boundary conditions, if we use it here, then we can find out these three constants, that is h, k and l. So now what is the displacement boundary conditions that we are going to use? So similar to the straight cantilever beam, if you have remember that at the fixed end, if theta equals to pi by 2 is our fixed end, so at b the fixed end v equals to 0 and dv dr, that is the any element in the vertical line will be 0. So which actually gives us h equals to 0 and l equals to pi d by e. So see, d is known to us. So these are the this is that same d that we have obtained from stress boundary condition. Now this d we know, so we know h and l. Now it is of our special interest that if we want to find out u at the free end of the curved cantilever, which you see is that theta equals to 0 at the free end. So u, the u displacement is actually L. So L is actually pi d by E. So we have found out L. So actually we will compare this. So now if we see that the cantilever that we have seen earlier, the upper end of the cantilever or the free end of the cantilever, u r theta is pi d by E. Now this d, if we substitute from the previous expression, so d is our from the previous expression, if I substitute d here, this is minus p a square b by n, where n is a square minus b square plus a square plus b square log of b by a. So if I substitute at the upper end of the this d, so this becomes minus p pi a square b square e into a square minus b square a by b, this. Now this is the if you see, this is the thing. So this is your, so at this point this is the radial line. So here this is the, there is a force. Now if you have solved this this problem, you have solved it with this, with h equals to 3 pi a cube, where a is the radius of this arc, and 3 pi a cube p into e by h cube. H is the depth, and b is actually 1 for us because we have taken the unit thickness. Now which actually here is this is the general formula from the elasticity solution, where we have used two-dimensional expression. Now if b tends to a for this solution, that b tends to a means that the thickness of the beam becomes small. So that thickness is b minus a is very small compared to a. Then we can write log b by a is log of 1 plus h by a. and this can be expressed in the series terms, which is this, and then we consider we substitute this here, and after substitution here, if we after substitution here we neglect the higher order terms of h, that is h square or h cube in the top. So it's so that means the small, because h becomes small, so cube becomes small, square becomes small, and 4 becomes small. So if we neglect those higher order terms, then we get the solution this. So this is same what we have got from the strength of material approach. So in a sense, what we have shown here, that this is a elasticity solution and this is the strength of material solution. So elasticity solution for a special case can be considered as a strength of, a solution of the strength of material. So this approach, elasticity approach, gives you more refined solution, where strength of material solution gives in general more coarse solution or the approximate solution, but elasticity solution gives you more fine or refined solution or more detailed solution of the problem. So this essentially means that if we want to study a complicated body or the complicated stresses involved, we need to solve the elasticity solution, and it depends, we need to go for the elasticity solution for detailed study, and then that does not mean that strength of material solution is no use, because strength of material solution often very well approximate the exact solution. For instance, the Wrinkleback formula, what we have seen in the strength of material solution, is very well or very accurate compared to the elasticity solution of the pure bending of the curve beam, that we can verify. So that means the strength of material solution is also very important, and this is in a nutshell completes our flexure part of the problem. So I will just briefly summarize what we have done here. In the first lecture, what we have done, we have introduced the basic two-dimensional differential equation, compatibility equation, and then the stress function, the differential equation in terms of stress function. The stress functions, we have also shown that if there is a body force, constant body force, or there is no body force, the stress function, what is the form of the body force, and what is the form of the compatibility equation, and then the stress function. Now this stress function leads to a biharmonic differential equation for a rectangular Cartesian system as well as polar coordinate system. So with this biharmonic solution of this biharmonic equation with the proper boundary condition gives us the solution of the elasticity problem. Now this the solution will be in terms of stresses. So boundary condition will be in terms of stresses. So first, what we have done, we have solved a plane cantilever, straight sided cantilever with a vertical force, and then we checked several stress functions, and first we solve it through intuition from the strength of material knowledge, where we can compute the stress functions, we can approximate the stress functions from our intuition, and then solve the stresses by solving the biharmonic equation properly, and then use the stress boundary condition to solve it to find out the constants. Now in the next class, what we have shown is that it is not only, you need not to only use your intuition or your strength of material knowledge, you can actually superimpose the different stress functions, which indicates different stress states of the material, and then using the property of linearity or the linear differential equation here, the biharmonic equation, we can again solve the problem and we get the same answer. Now, once we solve the stresses, then we go for the displacement. Now, it is interesting to point out once again here that in this procedure, when we solve stresses, the stress of the body does not involve any material. So, that means the constitutive behavior is independent of the stress solution. So, that does not mean that it is not important, because when we find out strains and then the displacement from the body, displacement from those stresses, then we need to invoke the material laws or constitutive laws, and then the material constants comes into picture. So, essentially the strain and stress we find out, and then from there we integrate for finding out the displacements u and v, and then we again use the displacement boundary condition to find out the displacement to find out the constants, and then we find out the displacement. So, in the next what we have shown the pure bending case, where the pure bending case is essentially the we have solved in strength of material via Winkler-Bach formulation. That Winkler-Bach equation gives us the hyperbolic stress variation, and here with the elasticity approach we have solved this problem, and it can be proved that Winkler-Bach actually very well approximate the elasticity solution, while the linear stress pattern does not approximate at all. So, the error is much more here. Now, in the next case, similar to the first case, we have also considered a curved cantilever, and this curved cantilever is acted with the horizontal force P, and this P is essentially, this problem essentially we have solved in the strength of material approach. So, we then compared this deflection of the free end of the via strength of material approach and the elasticity approach. We find that strength of material approach is a special case of the elasticity approach, when the thickness goes to thickness is much less than the radius, inner radius of the cantilever beam. So, this completes our flexure formulation, and in the next module we are going to start the torsion problem. So, thank you.